So next law, law of multiple proportions. It states that when two elements combine together, to form two or more compounds, then the ratio between different masses of one element which combines with the same mass of other element is a simple whole number ratio. Now write down example 1. I'll start with easy example and then we take up a slightly complicated example. Elements, hydrogen and oxygen. Please keep on writing and keep on understanding what I'm explaining here. See, in this law, we'll talk about only two elements, neither less than two elements nor more than two elements. I've taken two elements, hydrogen and oxygen. Now, these two elements should be such which combine together and form a minimum two different compounds. They can form two or more than two compounds, but minimum two compounds. Now, we consider compounds formed by hydrogen and oxygen. Compounds, water and hydrogen peroxide. Now, hydrogen in water is 2, oxygen is 16. This is the contribution in the molecular weight, right? In hydrogen peroxide, hydrogen is 2, oxygen is 16. Oh, sorry, 32. Oxygen is 32. Now look here. We'll use the definition of law of multiple proportions, and then I'll tell you what this law means. See, you can see different masses of oxygen, 16 and 32. Different masses of oxygen are combining with the same mass of oxygen in these two compounds. Ratio between different masses of oxygen which combine with the same mass of hydrogen is a simple whole number ratio. That's what is the definition. I'll again speak the definition for you. Definition, law of multiple proportion says that ratio, look at my finger where I'm pointing, ratio between different masses of one element which combine with the same mass of the other element is a simple whole number ratio. Now, example 2. I'm taking examples of carbon and oxygen as two elements. They'll combine to form compounds. Carbon monoxide and carbon dioxide. Carbon in CO is 12, oxygen is 16. In carbon dioxide, carbon is 12, oxygen is 32. Different masses of oxygen which combine with the same mass of carbon bears a simple whole number ratio. And if this is a simple whole number ratio, it means this ratio proves the law. Now, third example in which we'll have to do some calculation, slight calculation. I'm considering elements iron, and oxygen. Iron and oxygen combine to form two oxides, ferrous oxide and ferric oxide. So these compounds are FeO, Fe2O3. FeO is ferrous oxide, Fe2O3 is ferric oxide. Atomic weight of iron is 56. So 56 combines with 16. In the second case, 112 combines with 48. Mass of none of the two elements in these two compounds is same. This is not same, this is not same. It means now we'll have to do some calculation. I'll not change one of the two. Let us say 56, 16. In the second case, I'll do some calculation. A simple unitary method. Simple unitary method. Look here. 112 combines with 48. 1 combines with 48 divided by 112. And 56 combines with how much? That you can calculate. I'll repeat. 112 grams of iron combines with 48 grams of oxygen. So 56, same mass, will combine with how much of oxygen that I'll calculate. It will come out to 24. Now, same mass of iron is combining with different masses of oxygen. I'll take the ratio of these two masses. This ratio is a simple whole number ratio, 2:3, and therefore it proves the law. Right? Slight calculation was required. But remember, in this law, you'll come across some complicated numericals as well, which you'll find in my assignment sheets, worksheets. We'll take last one more example. This is example number 4. I'm considering two elements, nitrogen and oxygen. Nitrogen and oxygen combine together to form many compounds. NO is called nitrous oxide. NO is called nitric oxide. N2O is called nitrous oxide, also called laughing gas. Then NO2 is called nitrogen dioxide or nitrogen peroxide. Then N2O5 is called nitrogen pentaoxide. We'll take one more, N2O3. This is dinitrogen trioxide or nitrogen trioxide. Now, nitrogen and oxygen, 14 and 16. This is 28 and 16. This is 14 and 32. This is 28 and 80. And this is 28 and 48. Now you can, as we did in the previous case, we fixed the quantity of iron at 56 and 56. Remember, you can fix the quantity of any one of the two elements, and that too at any level you want. I fixed for 56 and 56. You could have fixed at 1 gram, 1 gram, 10 gram, 10 gram. It's your choice. But you have to carefully think, if I fix at a particular quantity, particular level, when I'll have to do minimum calculations. In this case, you can see 14, 28, 14, 28, 28, and these values, they are in front of you. Can you tell me when I'll have to do minimum calculations? For minimum calculations, which of the two elements should I fix and at what quantity should I fix? Can you suggest? I'll repeat. For minimum, yes.
So you should fix nitrogen
At, correct, nitrogen at
Sir,
what
at
level?
28.
Yes, yes, that will be the minimum calculation required. So in this case, no change. In this case, no change. In this case, no change. Now, 14 combines with 16, it means 28 will combine with 32.
32.
14 combines with 32, it means 28 will combine with 64. Same mass of nitrogen combines with different masses of oxygen. Take ratio of all these different masses of oxygen, it's clearly visible. It's a simple whole number ratio. So this ratio will be this will be 2:1:4:5:3. So this is a simple whole number ratio. But generally, when you get numericals in exam, only two compounds are considered being formed by two elements. And there are very interesting numericals. You have all the assignment sheets with you. Solve more and more yourself, you'll learn more. So we have finished three laws. First and second were almost nothing, law of conservation of mass. Second, law of definite proportions. In the third law, which we finished just now, there of course was something to do, and there'll be much more to do when you solve numericals on multiple proportions in my assignment sheets. Now coming to fourth law. Lussac's law of combining volumes. I'll read it out for you. Gay-Lussac's law of combining volumes. Just write the statement. In fact, you'll understand the definition only when we take up examples, right? It states that the ratio of volumes of various gaseous reactants consumed and gaseous products formed is a simple whole number ratio provided all measurements of volumes are done under similar conditions of temperature and pressure. For example, now just forget what the definition you have written. You'll be able to understand only when I explain with the help of example. We'll take the example of N2 gas plus 3H2 gas. You also write it example 1. N2 gas plus 3H2 gas gives 2 ammonia gas. This is a very important reaction. Industrial growth of any country depends on the quantity of ammonia manufactured in that country. Industrial nahi, agricultural growth. This process is called Haber's process, Haber, Haber's process. Okay. I'll go a bit slow so that you can understand. This is 1 mole, this is 3 moles, and this is 2 moles. And all are gases. If you remember, I taught you about molar volume in this chapter. So if I take 1 mole of nitrogen at STP, this will be 22.4 liters of volume. If I take 3 moles of hydrogen, it will be 22.4 into 3 liters of volume. If I consider ammonia, 2 moles of ammonia will be 22.4 into 2 liters of volume. It means the ratio of volumes of these gases consumed and this gas produced. I'll repeat, ratio of volumes of these gaseous reactants consumed and this gaseous product formed. This ratio is a simple whole number ratio, 1:2:3. And if you look at it carefully, this ratio is nothing but the ratio of these numbers which are used to balance chemical equations. And these numbers used to balance chemical equations are called stoichiometric coefficients. I'll dictate you later what is stoichiometric coefficient. This is the term used for them. So I'll repeat, ratio of, now coming back to the statement, ratio of volumes of gaseous reactants consumed and gaseous products formed is a simple whole number ratio, provided there is a condition, provided all volumes are measured at same temperature and pressure. Means at whatever temperature I measure volume of one gas, at the same temperature and pressure, I will measure volume of all other gases. Like in this case, all measurements were done at STP, standard temperature and pressure. I'll take one more example. This is combustion of methane. CH4 gas plus 2O2 gas gives CO2 gas plus 2 water liquid. Now, remember one thing, this law is only for gases. This law is only for gases. In this case, one product is a liquid, water. So when we take the ratio, water will not be taken into consideration. In the previous example, I told you, ratio will be nothing but the ratio of stoichiometric coefficients. It means ratio of volume of methane and oxygen consumed and volume of CO2 produced will be 1:2:1. Now, how do I apply it? How do I apply it for solving numericals? Listen verbally, it's very simple. I can say when 1 liter of methane is consumed, double means 2 liters of oxygen will be consumed and 1 liter of CO2 will be produced. If I say 10 liters of methane is burnt, 10 liters of methane is consumed, for that 20 liters of oxygen will be consumed and after the reaction 10 liters of carbon dioxide will be produced. Will not take water into consideration because we are considering only gaseous reactants and gaseous products. Condition again remains the same. Temperature and pressure at which volumes are measured should be same for all reactants, all gaseous reactants and gaseous products. Now, based on this, I'm sharing one numerical, but before that, we'll solve one numerical on multiple proportions. Then we'll solve one numerical on Gay-Lussac's law. First, I'm sharing numerical on multiple proportions. Check your WhatsApp message. This is numerical law of multiple proportions. It says that 3.5 grams of nitrogen gave 7.5 grams of an oxide on reaction with oxygen. 4.6, I'll read in parts and then write. Nitrogen oxide number 1, 3.5 grams of nitrogen gave 7.5 grams of its oxide. These are masses which I'm writing. On reaction with oxygen, it means oxygen will be 7.5 minus this 4 grams. 4.6 gram of another oxide of nitrogen. So this is oxide number 2 and weight is 4.6 grams. Gave 1.6 gram of nitrogen on reduction. Sorry, 1.4 gram. What is reduction? Reduction is nothing but removal of oxygen. And after removal of oxygen, nitrogen is left, right? So nitrogen is 1.4 and remaining was oxygen. This minus this, 3.2 oxygen. Now, I'll fix the quantity of one of the two elements. Let us say I do not change this. I change this one. Simple unitary method. 1.4 combines with 3.2. 1 combines with 3.2 divided by 1.4. And 3.8 combines with how much? When you calculate, this will come out to 8. Same mass of nitrogen combines with the different masses of oxygen. And the ratio of these masses is a simple whole number ratio. And therefore, this proves the law.
Won't it be 3.5 multiplied by 3.5?
Oh,
So
yeah.
there, sir.
3.5. 1.4 combines with this 3.2. Yes, 3.5. So this will come out to 8. Ratio will be a simple whole number ratio. Now we'll take up one numerical on Gauss' law. You'll find this numerical as Intext Numerical-15 in the. I'm not uploading in the chat box. You'll find in the description box of the video. Check this one. Yes, numerical says calculate volumes of butane and oxygen required to produce 12 liters of CO2 gas. It means we are burning butane, and for burning butane, oxygen is required. So first we'll write balanced chemical equation for the combustion of butane. Butane is C4H10. For burning, oxygen is required. Remember, when we burn any hydrocarbon, products are carbon dioxide and water only, nothing else. So products are CO2 and water. Now, how to balance without wasting time? 4 carbon will give 4 CO2, 10 hydrogen, half of 10 is 5. 10 hydrogen will give 5 water. After that, this is 8 oxygen plus 5 oxygen, total 13. On the left hand side, this will be 13 by 2. You can use 13 by 2 or you can multiply the entire equation by 2 so that you get whole numbers. Even like this, you can use, there's no harm at all. Question is, calculate volumes of butane and oxygen required to produce 12 liters of CO2. Water is a liquid, water is not considered here. Rest everything is gas. See, according to the equation, ratio is 1:13/2, that is 6.5:4. So I can use unitary method. For 4 liters CO2, for 4 liters CO2, methane required is equal to 1 liter. For 4 liters, methane required is 1 liter. For 12 liters, how much butane is required? That you can calculate 1/4 into 12, 3 liters. This is one answer. Now, second part, oxygen. For 4 liters CO2, O2 required is equal to 13/2 liters. For 12 liters, how much oxygen is required? 13/2 divided by 4 multiplied by 12. When you calculate, this will come out to 19.5. So these are two answers of volume of butane required and volume of oxygen required to produce 12 liters of carbon dioxide. Right? Now we take up the next law. Before we take up the next law, we'll take up one hypothesis. Can anyone tell me what is the difference between law and hypothesis?
A law is a proven fact, whereas a hypothesis is an assumed.
Yes, very good. So hypothesis is something which is just proposed that this is happening, this should happen. But if it is experimentally proved, it becomes law. In case it is not proved, then it remains hypothesis. So in one sentence, we'll take one hypothesis just to honor the person who initiated this. Right on. It is Berzelius hypothesis. Berzelius. Berzelius hypothesis. In fact, this hypothesis failed just because of one word, but that word made a lot of difference. It states that equal volumes of all gases under similar conditions of temperature and pressure contain equal number of atoms. Underline the word atoms, and this was the drawback of this statement. Equal number of atoms. Next paragraph. It was later modified and proved by Avogadro. So today what we study is Avogadro's law. We do not study Berzelius hypothesis. But Avogadro's law came into picture only on the basis of Berzelius hypothesis. So right on, next law we are starting now. Avogadro's law. Same statement, only one word will change. In Berzelius hypothesis, it was atoms. Now it will be molecules. That is the only difference. That it states that equal volumes of all gases under similar conditions of temperature and pressure similar conditions of temperature and pressure contain equal number of molecules. Contain equal number of molecules. I'll first explain, then we'll again come back to numerical. Only numerical will be asked. Statement nobody is asking in the exam. But before that, let me explain. You need not draw anything. You just try to understand what I'm explaining here. Let us say we have two vessels. Both the vessels have same capacity, V liter. Let us say this has nitrogen gas, this has hydrogen gas, same volume. Both are maintained at the same temperature and same pressure. Let us say in both the vessels, pressure of the gas is 0.5 atm. Let us say temperature of gases in both the vessels is also same. Let us say temperature is 25 degrees centigrade. Right? At the same temperature and pressure, okay, so two gases, same volume at the same temperature and pressure. Law says both will contain same number of molecules. If this contains n number of molecules, this will also contain n number of molecules. Now let me justify on the basis of an example which you'll be able to understand. Let us say I have two vessels. Both the vessels have a capacity of 22.4 liters. This contains nitrogen, this contains hydrogen. And both the vessels are maintained at STP. STP means both are maintained at standard temperature of 0 degrees centigrade. Both are maintained at standard pressure of 1 atm. Both have the same volume, 22.4 liters. Now, if you recall molar volume, 22.4 liters of any gas at STP will be 1 mole. It means in these two vessels, there's 1 mole of nitrogen and 1 mole of hydrogen. And 1 mole of nitrogen, 1 mole of hydrogen contain same number of molecules, that is Avogadro's number. Now, consider this second vessel is 44.8 liters and this vessel is 22.4 liters. Capacity of this vessel is double than the capacity of this vessel. Rest everything is same, temperature and pressure is same, only the volume has doubled. Naturally, 44.8 liters means 2 moles of the gas. 2 moles of the gas means number of particles, number of molecules will be 2 into Avogadro's number. This is 1 into Avogadro number. This will contain 2 into Avogadro's number. Right? So if volumes are same, number of particles, number of molecules will be same. Naturally, if volumes are double or 1.5 times or 2.5 times, accordingly, number of molecules in the given volume will change. Now we'll solve one numerical in which both Gay-Lussac's law and Avogadro's law both will be used together. See this, Michael. 2 liters of ethane contains 4 into 2 liters of ethane contains 4 into 10 power 22 molecules at a particular temperature and pressure. On combustion, CO2 produced is collected at the same temperature and pressure. Predict the volume of CO2 produced and number of molecules it contains. Now here in this numerical, he's talking about ethane which is being burnt. I'll write the equation for combustion of ethane. C2H6 plus O2 gives CO2 plus water. 2 carbon will give 2 CO2. Half of 6 will be 3. 3 water. 4 plus 3, 7 oxygen means 7 by 2. Except water, remaining 3 are gases. Gas, 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 and this is liquid. This is ratio is 1, 3:2, and 2. Now, numerical says 2 liters of ethane contains 4 into 10 to the power 22 molecules at a particular temperature and pressure. On combustion, CO2 is produced and we have to calculate, predict the volume of CO2 produced and number of molecules it contains. So it's very simple. If you think in terms of Gay-Lussac's law, 1 and 2, ratio is 1:2. It means if 2 liters of ethane is burned, how many liters of CO2 will be produced? Ratio is 1:2. It will be 4 liters. So volume of CO2 produced is equal to 2 into 2, that is 4 liters, according to Gay-Lussac's law, GLL. According to Gay-Lussac's law, 4 liters will be produced. This you should specify. 1. Second, now we'll apply Avogadro's law. Avogadro's law says equal volumes at same temperature pressure contain equal number of molecules. Now 2 liters contains 4 into 22, 4 into 10 to the power 22 molecules. It means, 2 liters contains so many molecules, then 4 liters of this should contain double. So number of CO2 molecules will be 4 by 2 into 4 into 10 to the power 22. 8 into 10 to the power 22. This is according to Avogadro's law. Right? Volume is double compared to this. It means number of molecules will be double compared to this. 8 into 10 to the power 22 molecules. Right? Now, we are beginning the most important part of this chapter, although complicated things will come next time. You know what is a chemical equation. You should know the definition, although that definition is never asked. Then we'll solve numericals based on chemical equations. Right on. Chemical equation. Chemical equation. See, like here I've written this is a chemical equation. But if you're asked to define chemical equation, what will you say? Right on. A chemical equation is the symbolic representation, because we represent in the form of symbols, symbolic representation of an actual chemical change. An actual chemical change. Remember, we should write chemical equation only for that reaction which actually takes place. If you think of gold reacting with water, hypothetically, you can write that gold plus water leads to formation of gold hydroxide plus hydrogen. But gold does not react with water. So definition says an actual chemical change. Continue. It should be balanced. It should be balanced in order to satisfy the law of conservation of mass. Law of conservation of mass. And you know what is the meaning of balancing a chemical equation? Balancing of chemical equation means making number of atoms of each element equal on reactant as well as product sides. That is called balancing of a chemical equation. And why do we balance a chemical equation? Just to satisfy the law of conservation of mass, law of conservation of matter. Now, any calculation which is done on the basis of a chemical equation without applying Gay-Lussac's law or Avogadro's law, those calculations are called stoichiometric calculations. So write on the heading STOICHIO metric, stoichiometric calculations. Just write the meaning. You can even call it definition. Right. Calculation of amount of various reactants consumed and products formed on the basis of a balanced chemical equation is called stoichiometric calculation. Is called stoichiometric calculation. For example, consider burning of methane. Consider burning of methane. So first we'll write the equation for burning of methane and then balance it. CH4 gas plus O2 gas gives CO2 gas and 2 water. It's a liquid. I've already balanced this equation. Now look, what is the information conveyed by this balanced chemical equation which can be used for calculations? I'll write below each and every reactant and product. One, I can say that 1 mole of methane reacts with, sorry, this is 2O2. Please, this is 2O2. So I can say 1 mole of methane reacts with 2 moles of oxygen to produce 1 mole of CO2 and 2 moles of water. I can also say that molecular weight is 16. I can also say that 16 grams of methane reacts with 2 into molecular weight, 64 grams of oxygen to produce 1 into molecular weight, that is 44 grams of carbon dioxide, and 2 into molecular weight, that is 36 grams of water. If you think in terms of law of conservation, this total is 80 and this total is 80, right? I can also say this is gas. I can say 22.4 liters of methane at STP reacts with 2 into 22.4 liters of oxygen at STP to produce 22.4 liters of carbon dioxide at STP. In this statement, we will not include water because water is a gas, it is not a liquid. Now, this data we can use in cross way. See, I can say 16 grams of methane produces 22.4 liters of carbon dioxide. I can say 22.4 liters of methane produces 44 grams of carbon dioxide. I can also say that Avogadro number, 1 mole means Avogadro number of molecules of methane react with 2 into Avogadro number of molecules of oxygen to produce Avogadro number of molecules of CO2 and 2 times Avogadro number of molecules of water. So you can use the data in any way, any form you want. So this is just the introduction about stoichiometric calculation. Proper stoichiometric calculations will start in the next class, right? Right till then, as far as today's assignment is concerned, I'll solve properly. It will be a lengthy video. There was no point wasting half an hour in explaining that simple assignment. So I'll make a video, upload in the next week, right? Right till then.
Thank you, sir.